In this section, we are going to cover electromagnetic switches and their uses and operations in motor control circuits. We'll also cover protective type switches used, as their name implies, to protect electrical circuits and the machinery controlled by these circuits. So, let's start by defining these control elements. Electromagnetic devices are used in electrical control systems to switch, either directly or indirectly, the on-off operation of lighting and power loads, such as motors. These devices are called electromagnetic because they use a magnet and electrical power to actuate the switching mechanism. The electromagnetic control devices we'll cover, which are used in the control of motor operations, include contactors and magnetic motor starters. The devices we'll cover, which protect the motor and the motor circuit, include fuses, breakers, and overloads. Let's start by looking at contactors. Magnetic contactors, as the name implies, also actuate their contacts by energizing a magnetic coil. In fact, contactors operate in a very similar fashion as control relays, except that relays are used for general-purpose control switching of light-duty loads, while contactors are used for the switching of lighting systems, heaters, transformer loads, which are inductive, and other capacitive loads. Although there are several types of contactor assembly designs, all of them operate in a very similar manner. When voltage is applied to the magnetic coil, the armature is attracted and forces the movable contacts to make connection with the stationary contacts. Magnetic contactors are available for single-phase and three-phase AC voltages, as well as for DC voltages. Contactors for each of these three categories are rated according to NEMA or NEMA, to specify the size of the load that they can handle safely by each contact in the contactor. The sizes range from 00 to 9, according to the horsepower of the load and the voltage being switched. For example, a NEMA 2 contactor is used when you need up to 45 amps continuous current. This contactor could be used in a 15 or 25 horsepower load application of a 208, 240 or 480 voltage system, respectively. The single-phase NEMA 00, 0, 1, and 2 ratings are only available to 120 and 240 volt systems from 1/3 to 7.5 horsepower. The standard rating available for DC contactors are from size 1 to 9, with current capacities ranging from 25 amps to 2500 amps. The coil in the contactor indirectly controls the operation of its load. That is, when the coil is turned on, its high-power contacts close, therefore providing power to its load. For example, this three-phase, three-pole contactor connected to a three-phase heater will give power to the heating elements once there is control power to the coil. This control power may be 120 volts AC, while the power provided to the heaters through the power contacts could be 480 volts. Contactors are represented in ladder diagrams with this symbol, very similar to a relay. Its power contacts, however, are not represented in the ladder diagram, but in another electrical diagram called the wiring diagram. These contactors also have what's known as auxiliary contacts, which react in the same manner as control relay contacts and are not part of the power contact circuit. We could graphically represent a contactor circuit like this, where the three-phase power lines are being switched to the heater. When the switch closes, the contactor's coil is energized, thus closing its power contacts and turning on the heater. The auxiliary contacts of the coil will also close, which, if contacted to a light, will make it light up. Obviously, this type of circuit representation is cumbersome and confusing. That is why we simply represent it like this in the ladder diagram for control purposes, and like this in a wiring diagram. Even though AC and DC contactors operate in a similar manner, there are some differences between the two. In DC contactor applications, we may switch only one of the power lines, thus requiring only one set of contacts, or a contactor having only one pole. In three-phase circuits, it is necessary to switch all three lines, thus requiring three poles. The magnetic or coil assembly of a DC contactor is made of solid steel instead of laminated steel, as in the case of the AC contactor. The reason being that DC current only flows in one direction continuously and doesn't create eddy current problems. The other major differences are the electrical and mechanical requirements to suppress the arcing created during the opening and closing of the contacts. We'll touch on this subject next. Although the contacts and contactors are constructed of strong cadmium oxide and silver metals to fight corrosion and wear, they are still subject to arcing that is present during the opening and closing of the contacts. This electric arc is created because during the closing or opening of the contacts, there is a very short time in which the contacts are neither closed nor open, and the breaking of the current, which causes heat in the contacts, creates enough, so to speak, metal vapors between the gaps of the contacts, which are still trying to conduct current. This creates the arc. This arc can continuously create heat, which can eventually damage the contact surface. Since prolonged arcing can damage the contacts, the sooner this arcing is extinguished, the longer the contactor will last, and there are several methods used to suppress the arcing. Suppression of DC arcing is harder to eliminate because the DC supply continuously provides flow of current in one direction instead of fluctuating, like DC does, between positive and negative. The DC arc will last until the two contacts are so far apart that the arc extinguishes itself, and therefore there is more gap in between the two contacts. In contrast, AC arcs are self-extinguishing, thus having smaller space between the contacts. So AC contactors tend to run with less heat than DC contactors and have an increased contact life. Arcing is much more pronounced during the opening of the contacts because current is already flowing through the contacts, although it can also occur during the closing of contacts. There are three basic suppression methods used to extinguish and minimize arcing, and all electricians and technicians must be aware of them. Contactors provide, in one way or another, different types of arc protection, such as arc chutes and arc traps, sometimes incorporated in the cover of the contactor. The idea behind the chutes and traps is to confine, divide, and limit the arc as much as possible to a position away from the contact surface, thus providing an area in the contactor where the arc can be extinguished without damage to the contactor. Contactors may also provide a DC magnetic blowout coil for arc extinguishing. These blowout coils produce a magnetic field across the pole as current flows through the coil. This field interacts with the arc pushing up or blowing out the arc into the arc chute, where it is enlarged and extinguished. When a contactor has blowout coils, its power contacts are represented by this symbol. It is important to note that contactors should not be operated without their arc suppression elements, because damage can occur to the contactor or to the machinery or loads it is connected to. During preventative maintenance, make sure that the arc suppression features of the contactor are present and working properly without any damage. Troubleshooting contactors is done similarly to relays. You need to make sure that the coil is being energized and that the auxiliary contacts, as well as the power contacts, are responding to the coil's energization. Motor starters are one of the most widely used control devices in industry. As the name implies, they are used to control the on-off state of motors in a manner similar to the operation of contactors. In fact, the main difference between motor starters and contactors is the use of added protection devices for the motor to avoid overcurrents which could damage the motor under overload conditions. There are two types of motor starters: the manual motor starter and the magnetic motor starter. The manual motor starter functions like a switch which will connect the power lines to the motor by the activation of the switch, which closes the contact. The magnetic starter functions like the magnetic contactor, which uses a coil to activate the contacts. Both classes of starter have overload protection for the motor. A little later in this module, we are going to cover more on overloads in detail, but here we're going to go over their responsibility in a starter, which forms part of a motor control circuit. Motor starters are represented by this symbol in a ladder diagram, while its power contacts are represented like this. Motor starters also have auxiliary contacts which are used for interlocking connections with start-stop circuits and other components in a ladder diagram. The power contacts are generally represented in a wiring diagram where they connect to the motor being controlled. As we mentioned earlier, starters provide protection to the motor with overload relays, which are represented by either of these symbols. These overloads are encountered below the contactor section of the starter. The overload relay controls a normally closed contact, which is called the motor overload contact. The graphic representation of a magnetic starter and its overloads is like this, where the power contacts are shown at the top and the overloads are shown right below. The L1, L2, and L3 lines in a three-phase voltage system will be connected to the top of the starter, while the bottom will go to the motor terminals marked T1, T2, and T3. The coil of the starter, which energizes the power contacts and the auxiliary contacts, are represented in this configuration like this, while the normally closed overload contacts are graphically placed like this, in close proximity to the overload coils. In fact, this graphic representation follows very closely the actual location of the components that form the motor starter. At the top, we have the line power terminals. Below, the coil and the auxiliary contacts between these 2 points. The power contacts are sort of behind, while the overload relays and the normally closed overload contacts are right below. The overload protection is shown in the ladder diagram representation like this, where the normally closed overload contacts are right after the starter coil. These contacts will open if the overload relay detects that there is an overload situation which is causing the motor to pull more current. This can happen if the motor is experiencing a locked rotor situation, in which case the motor must be disconnected from the circuit, otherwise it could burn out. In this ladder circuit, the motor starter will be on if the limit switch closes. Note that the normally open auxiliary contacts close and turn the pilot light on. The power contacts will close, providing power to the motor as soon as the starter coil is energized. If the motor pulls too much current, the overload relays will trip and open the normally closed overload contacts, which in turn disconnect the motor from the circuit. Later, we'll see this overload operation in more detail. There are several types of magnetic motor starters, which are the full voltage, the combination starter, the reversing starter, the two-speed starter, and the reduced voltage starter. The full voltage starter is perhaps the most commonly used in industry. This motor starter is also called across the line because it switches the full voltage to the motor once the starter coil is energized. In the same cabinet or enclosure, combination starters provide a magnetic starter combined with a disconnect switch which can be fused or non-fused. This arrangement, provided by manufacturers, allows for a quick and convenient installation of a motor control in a single enclosure. Start-stop push buttons are also available in the front of the cabinet. Reversing starters are available for applications which require reversal of motor rotation, that is, forward and reverse. These reversing starters can be used with plugging switches in a circuit, as we'll see in a little while, to reverse the direction of the motor. We know that a three-phase motor can be reversed by simply changing any two of the three phases. The reversing starter provides the hardware to implement this reversal. This starter is composed of two contactor sections with their respective auxiliary contacts. These sections are used to switch the phases to the motor. The starter also provides the overload protection for the motor. The two-speed motor starter, as its name implies, provides two complete starters, that is, with two contactor sides and two overload relay assemblies to control two-speed motors. These speeds are low and high. Reduced voltage starters are available to control and allow a motor to start at a lower speed and then switch it to full speed. There are many advantages in using this acceleration method. There are four basic types or designs of reduced voltage starters. These are the auto-transformer, primary resistor, Y-delta, and part winding, each one providing advantages and disadvantages according to the application. The wiring connections made during installation of a motor starter must follow the manufacturer's wiring diagram specifications. As we know, ladder diagram descriptions will serve little purpose, if any, during the wiring and installation of a motor starter. Many times, especially applications requiring multiple motors to control a line, all starters are housed in motor control centers where they are easily accessed and available for troubleshooting. Of most importance during the installation is to make sure that the proper voltage phases are connected to the proper terminals. Remember that the reversal of phases can cause a motor to change rotation direction, and during startup, this could cause damage to the equipment or injury to personnel. Most motor starters are supplied from manufacturers with some pre-wiring. These include the wire that goes from one side of the starter coil to the normally closed overload contacts, and then from the other side of the overload contact to the return or L2 terminal connection on top of the starter. The other pre-wired connection is from one side of the auxiliary contacts labeled Terminal 3 to the coil. This side of the coil is where control power is connected to turn the starter coil on. As will be seen, these connections save a lot of time during installation of three-wire motor control circuits. Let's now look at plugging switches and their operation. Plugging switches are used to stop or break a motor rotation in a quick and fast manner. This switch is also called a zero-speed switch because it detects the rotation of the motor at zero speed or when it is close to stopping. In fact, the word plugging, as used in motor controls, relates to the stopping of a motor. A plugging switch is attached to the shaft of the motor pulley, turned by some part of the rotating equipment, and its shaft rotates with that of the motor. Inside the switch, there are two sets of double-pole, double-throw contacts, which open and close according to the direction of the shaft rotation. The mechanism that actuates these contacts is a centrifugal switch, which we'll see in operation in a second. The plugging zero-speed switch is represented by this symbol, where the circular arrow indicates a rotating type activation switch. We can graphically represent the speed of a motor like this, where the motor can go to full forward or reverse speed according to a motor control circuit. If we have a plugging switch attached to the shaft of a motor, the centrifugal force created by the rotation of the shaft will cause the forward set of contacts to close once the motor starts to go forward. The speed, or RPMs, at which the switch will close is adjustable. Let us assume that the contacts close in the forward motion around here and in reverse around here. In between this area, the switch contacts will be open. Once the motor starts and passes this speed, the forward contacts will close. If the motor is stopped, the switch contacts will be off after the motor is slowed down at this trigger speed. The simple operation of the plugging switch is used in interlocking circuits whenever we want to stop a motor very rapidly by reversing the direction of the motor. When we reverse the direction, the motor will obviously stop faster because it is going backwards. This section of the switch will allow the control circuit to detect when the motor is almost at rest and disconnect the circuit which caused the motor to go in reverse. The use of this switch has many applications in conveyor systems where you may want to avoid the coasting of a motor carrying parts and would rather want the conveyor to go to a sudden stop. This also applies in emergency stop circuits where a motor would be brought to a fast stop when necessary. Let's now turn our attention to protective type switches, which, as the name implies, protect circuits and equipment from potential damage. The distribution of electrical power in a plant can be very involved and complicated, and the circuits being supplied are subject to destructive overcurrents and short circuits. To protect these currents and the power system from blackouts, prolonged downtime, as well as from safety and freedom of fire hazards, fuses and circuit breakers are widely used. But how do they protect, and what do they protect? Let's first define what an overcurrent is. An overcurrent is a result of an overload current or a short circuit or ground fault current. The overload current is an excessive current relative to the normal operating current, which is confined to the normal conductive path provided by conductors, other components and loads, such as motors, that will form part of the power distribution system. We'll cover overload protection of motor loads in a little while. A short circuit or a ground fault current is an excessive current which flows outside the normal conducting path. While overloads are most often at no more than 6 or 10 times the normal current levels, short-circuit currents can be hundreds of times that of the normal operating current. This high current, if not cut off in a matter of a few thousandths of a second, will cause damage and destruction where severe insulation damage can occur. Additionally, it can cause melting of metal and conductors, vaporization of metal, ionization of gases and arcing, all of which can result in a fire. Fuses are used to reliably protect a circuit in which a short-circuit fault can occur. This protection is supplied by the design built into the fuse, which quickly disconnects the power being provided to a system. Fuses are represented by this symbol, which is a close resemblance of its original look. Inductive loads, such as squirrel cage motors, will pull between 6 to 10 times the amount of full-load normal current when they are first started. For example, a 200-volt 10-horsepower motor will pull 193.2 amps for a short duration before it reaches its full load amperage current. In this case, it pulls 6 times its full load current. When this circuit is protected with fuses against short circuits and ground faults, the fuse must be able to allow this overcurrent situation without breaking or disconnecting power to the motor circuit. There are single-element and dual-element fuses, each one used in particular applications. The single-element fuse, also called a non-time delay fuse, is made of one conducting element which has one or more links enclosed in a tube or cartridge surrounded by arc-quenching filler material. Under normal operation, the fuse conducts current simply by acting as a conductor. If an overload occurs and persists for a short interval, the temperature created by the overcurrent reaches a level which melts the link and a gap is formed, thus breaking the circuit. Whereas overload currents are normally in the 1 to 6, or, as in motors, 6 to 10 times the normal current, short-circuit currents are quite high. These single-element fuses may be subjected to a short-circuit current of 50,000 amps or higher. The response to these currents must be extremely fast to avoid serious damage and run the risk of fire. In fact, the response of a fuse must be within a matter of a few milliseconds in the event of a large ground fault. The single-element fuse, when exposed to these short-circuit conditions, will have all of its links melt simultaneously. The short-circuit current is cut off in less than half a cycle, or about 8.3 thousandths of a second, long before the short-circuit current can reach its full value. Single-element fuses provide excellent short-circuit protection. However, temporary and harmless overloads, like those created by motors, may cause nuisance openings unless the fuses are oversized. This will happen because if a fuse is sized to protect a motor circuit, it will trip during the inrush current generated at the start. On the other hand, if the fuse is allowed to withstand the inrush current, it will not provide adequate protection when a motor is running at full load current. For example, if the 10-horsepower motor circuit is fused to the maximum inrush current of 193.2 amps, it runs the risk of being burned out if an overcurrent exists, at, let's say, double its full load current for a period of time. The single-element fuse must be sized higher than the full load current of a motor in a circuit to allow the motor to start. The proper sizing of non-delay time fuses is specified according to the National Electric Code. To protect conductors and circuits from short-circuit and ground faults, we can also use dual-element time delay fuses. These fuses offer an additional feature of not only protecting against short circuits, but also they can protect motors from overcurrents due to stalling, overload, worn bearing, improper voltage, single phasing, and other possible causes. The dual-element time delay fuse works like this. It has 2 distinct overloads and short-circuit elements built in. If the fuse experiences a short-circuit overcurrent, the fuse will separate the links in the same fashion as the single element did. If the fuse experiences an overload condition for 10 seconds at about 5 times the value of the rated fuse, the overload element will snap out of the connector, thus disengaging the fuse from the circuit. This fuse allows motor protection from overloading. For example, if we had a dual-element fuse rated at 40 amps protecting a circuit of our 10-horsepower motor, we could sustain the overload inrush current of 193 amps at a little over 10 seconds before the fuse would open. In normal motor control circuit applications, the dual-element time-delay fuse, like this high-performance, all-purpose Bossman low-peak yellow, could serve as an invaluable motor-running backup protection to the motor starter overloads. This could be of particular help if a phase is lost or if the magnetic starter's overload contacts fail to open, but the power contacts remained closed because a severe overload has melted the contacts. In this case, the backup protection provided by the dual-element fuse will save the motor and circuit. If, during troubleshooting, a fuse is found to be open, it's a good idea to have it cut in half with a saw and determine if the cause of the opening was due to a short circuit or an overload. This could help tremendously to determine the source of a problem. When we talk about the National Electric Code, non-time delay and dual-element time delay fuses are rated under normal conditions in the range of 300 and 175% of the full load current of motors. This gives, for example, a non-delay time fuse only 3 times its rating to allow for the start of a motor. And we know that a motor may take at least 6 times the full load current when it is first started. The reason is that fuses do not open instantly at a current just above the fuse rating. As this graph describes a single-element and dual-element time delay fuse, rated at 100 amps, it will take 10 seconds for the time delay to open at a current of 500 amps, whereas it will take 2/10 of a second for the non-delay fast-acting fuse. You could use a non-delay fuse to protect a circuit if the motor inrush current could be sustained by the fuse during the inrush time. If the motor current passes this limit, the fuse will open. If this is the case, you may use a little larger fuse, up to 4 times the full load current according to code, instead of 3 times to protect the circuit. Otherwise, you'd be better off selecting a dual-element time delay fuse and provide adequate time for the inrush current. Let's take a quick example using both single-element and double-element fuses for our 10-horsepower 200-volt motor. This motor has a full load amperage rating of 32.2 amps. According to the National Electric Code, we could select a single-element non-time delay fuse of 90 amps to protect the circuit, according to Rule 430-52 of the Code. This fuse should be enough to let the motor start for a short duration. Remember that fuses, according to the curves, can allow motors to start if the motor start current curve does not trip the fuse. This 90-amp fuse does not provide protection for the motor under overload. Therefore, it would require overload protection at the starter. If we want to use a dual-element time delay fuse to protect the motor from overload, as well as the circuit from short circuits, we would select, according to Article 430-32 of the Code, a 40-amp fuse. This fuse will protect the circuit against short circuits, allow the motor to start when it pulls the starting inrush current, and protect it from overload conditions. In fact, if the motor overload relays are used in the motor control circuit, the dual-element fuses will serve as running motor backup protection in case the overload relays are the wrong size or fail to operate. This graph illustrates the motor damage curve and the protecting curve provided by the motor overload heaters. The dual-element curve is shown as backup protection. Additionally, the switch used in the dual-element circuit will be of smaller current carrying capacity than the one in the 90-amp circuit, therefore reducing space and money. Remember, a switch rating must be equal to or larger than the amperage rating of the fuse protecting the circuit. There are several types of fuses available according to the base it mounts in or the socket or adapter, as well as the interrupting current ratings. The basic division of fuse sizes is for 600 volts or less, and the other for voltages above 600 volts. Among fuses, there are also classes such as H, K, R, G, J, L, and T, which are rated for specific voltages and currents, depending on your application. These fuses will be placed in their respective holders. For example, these Class R rejection clips will accept only Class R type fuses. A circuit breaker, as defined by NEMA, is a device that opens and closes a circuit by non-automatic means if used as a disconnect, or that opens the circuit automatically on a predetermined overcurrent created by an overload or a short circuit. The circuit breaker trips a mechanism inside which disconnects the circuit from the overcurrent condition. The basic part of a circuit breaker, namely a circuit interrupter, is represented by this symbol for a single-pole, two-pole, or a three-pole circuit. This section of the breaker, which is the non-automatic, is followed by the automatic breaker section representation. Circuit breakers use two types of tripping elements, a bimetal or thermal and a magnetic, and in some cases both. These devices may trip in an instantaneous manner or in what's called inverse time fashion. The inverse time simply means that the time it takes the breaker to trip is inversely proportional to the amount of current. The higher the current, the less time it takes to trip. For instance, a 20-amp breaker may take several minutes to trip a current of 25 amps, whereas if the same breaker is subject to a 50-amp current, it will trip in a fraction of a second. The bimetal breaker responds in an inverse time manner. As the current passes, it bends the bimetal and makes it trip. The magnetic type has an electromagnet element which responds to a high current generated by a short circuit. The activation in a magnetic breaker is instantaneous. Therefore, the most desirable is the breaker with bimetal and magnetic mechanisms. One element that responds to time delay and one that responds instantaneously. These symbols represent the thermal magnetic circuit breaker. Note that one side represents the bimetal or thermal mechanism, while the other one represents the magnetic component. In Part 2 of this program, we'll be covering motor overloads and how they protect motors, the controlling of motor operations, where we'll go over 2-wire and 3-wire controls, and finally, we'll review the causes that make motors fail.